Okay, so we are doing log functions. That's not good. Okay, who has heard of log functions before? No, a little bit? Okay, so we're gonna go over a few vocab throughout throughout this period. So logarithm. Okay. So I know this definition is kind of on the longer side, so I'll give you time to copy it down. And it might sound a little bit confusing right now, but I will show you what logarithm actually is in terms of the problem that we're using. So what is my basic exponential function? Y is equal to what? B to the power of x. So for my logarithmic, because exponential and logs, they go hand in hand. Logarithmic. This is x is equal to log b of y. So as far as what defines my logarithm, it's my x value. Because it says a number for a given base, so a number for a given base is the exponent to which the base must be raised in order to produce the number. So the next few examples we're going to practice bouncing from either exponential log or log to exponential. So you'll kind of see how they swap back and forth. So we have 16 is equal to 4 squared. If I'm looking at the 3, what is my base? Base is 4. My logarithm? 2. And then the number that I get is 16. So it's exactly how we did here, where you just move around your base, your logarithm, and your x, y, and b to fit that value. So in logarithmic form, it's 2 is equal to log base 4 of 16. Who thinks they can tell me what this is in logarithm form? Yeah, go ahead.
1.25 is equal to log of 16 times 32.
So it's, yeah, 1.25 is equal to log base 16 of 32. So for this, as far as this log statement here, this isn't log of 16 times, it's log base 16 of 32. Yeah. Is everyone good? So let's try it the other way around. Now for this case, what is my base? 5. And my logarithm? -2. So just working in opposite form, we have 1 over 25 is equal to 5 to the power of my logarithm, so -2. Go ahead and do that one. Okay. So what is this in exponential form? Yep, perfect. Okay. Since we're on base 10, here's another definition. So common logarithm, it's logarithm with base 10. So the reason why this is important though is just because a lot of times when you're working with log, you'll see just log of y. That's the same as writing it as log base 10 of y. Reason why, it's because a lot of our math, since we count in tens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then we kind of start over. Since tens are most common kind of set, they basically made it so they eliminate that 10 value from it. So for example, if we look back at number 4, this could also be written as log of 1000 is equal to 3. And if you don't, so basically saying if you don't see a number in the base, you have to assume, you can assume that it's 10. You automatically assume that it's 10. So another definition, it's kind of short. So natural logarithm with the base being e. This one is actually written as, so if you have something like x equal to log base e of y, you can rewrite this so it's equal to basically saying x is equal to ln of y, or natural log of y. So for example, if I wanted to if I had x equal to ln of 5, and I want to rewrite this in exponential form, how would I do that? So this is x equal to natural log of 5. If I were to rewrite it with log base e, what would this look like then? So if I wanted to rewrite it as log, it'd be x equal to log e to the y. E to the 5, thank you. And then that is 5 is equal to the power of e to the x. So yeah, a lot of converting back and forth is just swapping around your base and your base x and y's. Nothing really changes. Numbers really don't change. Okay. graphing. Okay. So you'll see some examples in your homework basically saying, here's my exponential graph, graph the inverse of it, based off the graph, so you're just swapping your points. So for example, what was the last one? Was 5? Yeah, we're on 6. So y is equal to 4 to the power of x. So in your homework, because you haven't learned how to quite solve for the inverse yet, I think that will be coming up probably when you get back. Do not quote me on that one. So in the homework, you'll be given basically the graph of y is equal to the power of 4x. What would my inverse points be? So if it's an inverse of each other, then what do I switch on my table? X and y, right? So what's one of my points? 1, 0, 1, so it's 1, 0. What's another one? So if this was 1, 4, then my inverse point is 4, 1. So your homework's going to ask you to graph the inverse of it. And I want to know what's my domain of my inverse function? X is greater than 0. What about my range? All real numbers. What about my asymptote? X is equal to 0. And my end behaviors. So for example, as x approaches 0, y is approaching what? Negative infinity. Okay. Then as x approaches infinity, y goes to infinity. Do a couple more. Who remembers what e to the power of 1 is? 2 point what? 2 point, not 2.5, not 6. If you round it completely, 2.7, yeah. 2.72 roughly. I only know that I introduced this because I talked about it last week. But either way. Same thing, we're gonna graph it, or they'll show you a graph. I want you to try to do the rest on your own though. So, yeah. Actually, this one we'll do together, just because e squared's kind of a weird number. Next one's gonna be doyo. Or however she calls it. Okay, so we know e to the power of 0 is 1. E to the power of 1 is 2.7. No, next one will be. And then e squared is roughly 7.7, I think. If I remember what I put in earlier. Oh, 7.4. Okay. So again, my graph is given to you. What are my inverse points? So we know 1, 0. What about this point? What's my inverse of it? 2.71. And then the other one, 7.42. Okay. So again, what's my domain? X greater than 0. Range, all real. Asymptote. Asymptote? Yeah. And my end behavior. So as x approaches 0, y goes to? Yep. And then x approaches infinity, y goes to infinity. Is there a pattern that you notice for the two problems that we did? Same end behavior. What about the rest? Yeah. Exactly. So they're all the same. If you notice basically that if they're both exponential growths, as long as they're growths, the inverse should kind of produce those same end behaviors. If there is a change, so if it's a negative sign or if it's a translation or anything of that nature, it could change that, or it will change that. But as simple as what we have here, we'll produce usually the same.